Now that we've considered some of the ways of adapting to climate change, we need to consider the bigger question: what can be done to limit climate change to reduce its future effects? The reason we started with adaptation is that dealing with the first physical effects of climate change is very much a design problem within the control of government, especially local governments, although an expensive and politically difficult problem to address. Limiting global warming is primarily an international, intergovernmental task. No significant progress can be made in slowing down and ultimately stopping climate changes without international treaties combined with strong enforcement at the national level. However, there are many ways to help reduce the ways that development of cities and suburbs contribute to climate change. In this course, we will talk about reducing the impact of automobile and truck traffic on the atmosphere by encouraging more compact, mixed-use, walkable neighborhoods and business centers. We will also describe the ways of limiting urbanization and keeping it to places where new development will minimize disturbance to the natural environment. However, as burning fossil fuel is a major contribution to climate change, let us now consider three alternative energy sources: geothermal energy, solar energy, and wind energy, and the ways that they can be incorporated into the design of cities and suburbs. As energy is lost through transmission via power lines, we will also consider both power plants and local sources as ways to bring alternative energy to individual buildings or local districts. Water and steam, heated by contact with the high temperatures of the Earth deep underground, closer to the planet's molten core, sometimes come to the surface naturally as geysers. The steam and hot water from a geyser can be harnessed to a power plant, which produces electricity without burning fossil fuel. This is one of the power plants that use this kind of geothermal energy. It's located in Sonoma County, California. Other places where power plants use energy from geysers include Iceland and the Philippines. In many places which don't have geysers, it's possible to use the heat buried deep in the earth to operate power plants, a process called deep geothermal. This diagram shows one way the process works. In this version, water is injected into a rock layer, flows through natural crevices, becomes hot, and then is extracted to power the plant. After use, it goes back into the rock layer and comes around again. An alternative, a deep pipe, uses a closed system that pumps fluid deep into the earth and then brings it heated back to the surface. Cornell University is experimenting with a deep geothermal installation to help reach its goal of achieving a carbon-neutral campus by 2035. As you see from the diagram, deep means 2 to 4 miles, depths that have become possible because of advances in drilling from oil and natural gas industries. This map, from a report by the National Renewable Energy Laboratory, shows that Ithaca, New York, where Cornell is not a part of the country most suitable for deep geothermal systems. The West is a better place for this technology, especially Texas and Montana. Given the high cost of installation, this is a technology most useful for whole urban districts or large institutions like Cornell. It could also power a generating station, although the loss of power from transmission then becomes a factor. Another form of geothermal energy, often called a heat pump, makes use of the temperature of the Earth about 4.5 to 6 feet down, 1.5 to 2 meters, which is constant at around 54 degrees Fahrenheit or 12 degrees Celsius. This is not heat from the Earth's core, but stored heat from sunlight. If you circulate a fluid down to that level, it will pick up the temperature of the Earth around it, which in summer will be colder than the air temperature and in winter often warmer. What the liquid does when it's pumped through the heating or cooling system is to boost its capacity so that it uses much less energy in creating a desirable temperature inside the house or building. Here's a photo of what it takes to put the necessary piping system in the ground. While there are vertical installations that take up less space, you still need to have open space adjacent to a building, although the pipes can be under a driveway or under a parking lot. This technology is commercially available right now. There's a high installation cost, but it will make the investment back in savings, although it can take up to 8 or 10 years. This technology may be more suitable for a school or other public building than for a house. If, however, financial incentives could be provided to homeowners, there could be a substantial decrease in the amount of fuel that would need to be burned. This would be the real reason for tapping geothermal energy. Harnessing solar energy using photovoltaic panels is making progress as an alternative power source. Here's a solar power installation in San Bernardino, California, and a somewhat different configuration installed in the Mojave Desert. This map shows the locations within the United States with the most potential for this kind of installation. You need both a reliable source of sunlight and plenty of room for the solar panels. This is a housing development in Freiburg, Germany, by the firm of Rolf Dietsch Solar Architektur, specialists in solar-powered buildings. Even in Freiburg, a very environmentally conscious city, you can see from the photograph that the surrounding buildings do not have solar panels. This is a street view of part of the complex. The interesting thing here is that the solar panels are arranged for optimal sun exposure, although the building actually faces east-west, not north-south. This charming photo shows a house in England with solar panels on the roof and other design features meant to create heat gain from sunlight. And this is a map of the United States showing the areas with the most potential for rooftop solar systems. It incorporates two major considerations: available sunlight and available rooftops. The big question with solar collectors for individual buildings: what happens at night or when the sun doesn't shine? The answer right now is that the building remains connected to the power grid, and it draws on it to make up power deficits when the solar panels don't provide enough electricity. Some states have a requirement that power companies buy excess power from building owners who want to sell it, and the building owners can buy electricity when they have to. This arrangement is not popular with the utilities. It's not a big problem for them now, but it could become one if surplus solar power from individual buildings were to make one of the utilities' existing expensive power stations redundant. Nowhere near this happening anywhere yet. Fortunately, there's an alternative. The development of electric cars has led to a big improvement in the storage capacity of batteries, and these batteries are becoming available to store electric power from solar collections. The advantage of the combination is that there are no transmission losses. If every building became self-sufficient in meeting its energy requirements, it could lead to a huge reduction in the need for power plants that burn fossil fuel. Energy from wind power is another alternative to fossil fuels, either offshore, as here in Denmark, or this onshore installation in Oregon, USA. This map of the U.S. indicates that the best wind farm locations are either offshore or on the Great Plains. Small-scale wind turbines, a familiar part of many farms, have now been configured so they can be incorporated into small-scale buildings. This tower in London by BFLS Architects was the first large building to incorporate wind power generation. If this technology becomes available on a large scale, it could lead to zoning cities for wind power, which could mean restricting tall buildings to the places with the best wind access. Okay, here's a question for you. Do you or does anyone you know make use of alternative energy sources at home or for your business? If so, how well does it work? Do you plan to use alternative energy sources yourself in the future? About 5% of the energy generated in a power plant is lost in transmission between the plant and the user. This is one reason why alternative power sources generated in a local district can be a better alternative. A second reason is that installation costs for geothermal, solar, or wind energy can be shared among many users in a district. Larry is going to talk about the district model for utilizing alternative energy sources in the next segment of this course.